Let us continue with the lecture. For this part of the video, we will be defining the derivative of a vector function. So let R be a vector-valued function whose coordinates are given by x of t, y of t, and z of t. The derivative of this function R is defined as the limit of R evaluated at t plus delta t minus the vector R of t divided by delta t as delta t tends to 0, provided that this limit exists. The derivative of R is denoted by R prime of t. Now let us consider the geometric interpretation of the derivative of a vector-valued function. So let us look at this image on the right side of the slide. This black curve here represents the curve of R of t. Now, the two red vectors are the vectors R of t and R evaluated at t plus delta t. So if we form the difference between these two vectors, we get this blue vector here. So let us take a point t0 in the domain of R. Now, observe that this difference of two vectors R evaluated at t0 plus delta t and R of t0 and the same vector divided by delta t are parallel. This is so because one vector is just a scalar multiple of the other. Now note that as delta t tends to 0, this vector here, this blue vector here, tends to this pink vector, which is R prime of t. So in other words, as delta t tends to 0, the vector R evaluated at t0 plus delta t minus R of t0 divided by delta t, which is parallel to this vector here, to this blue vector here, this vector approaches a vector that is tangent to the graph of the function R at t equals t0, which is this pink vector here. Now some remarks. For a point t0 in the domain of R, the vector R prime of t0 is tangent to the graph of the vector function R at t equals t0 in the direction of the curve. Now let us recall that R prime of t is given by the limit of this difference divided by delta t. Now let us suppose that R of t is given by the functions x of t, y of t, and z of t as the coordinates of R. So plugging in these functions to R of t plus delta t, we see that this limit becomes limit of x of t plus delta t, y of t plus delta t, and z of t plus delta t minus the vector x of t, y of t, z of t all over delta t. Now we can perform the difference in the numerator, the subtraction in the numerator, and so the numerator becomes x of t plus delta t minus x of t. That will be the first coordinate, but we have a delta t in the denominator, so the first coordinate becomes limit of x of delta t plus x of t plus delta t rather minus x of t divided by delta t after distributing the limit to the coordinates. So similarly, we have this expression for the second coordinate and the same expression for the third coordinate. Now let us look at the first coordinate. Isn't this limit familiar to us? This is simply the derivative of x of t. And so the first coordinate is x prime of t, the second coordinate is y prime of t, and the third coordinate is z prime of t. And so we have this result that if R is given by x of t, y of t, z of t, and the derivatives of each component of R are existent, then necessarily the derivative of R is given by the vector valued function x prime of t, y prime of t, z prime of t. So let us look at an example. So here, the vector valued function R is given by the vector valued function ln of t, tanh of t, sine inverse of t. Okay, so let us compute for the first derivative of R and the second derivative of R. Okay, so what we need to do here to get R prime of t is to differentiate each component of R of t. So first, what is the derivative of ln t? We have 1 over t. Now, for tanh of t, the derivative is sec squared of t. And finally, for the derivative of sine inverse of t, we get 1 divided by the square root of 1 minus t squared. Now, to obtain the second derivative of R, we just need to get the derivative of this vector valued function R prime of t. And so, we will have the second derivative of R at t is the vector valued function whose coordinates are negative 1 over t squared. Okay, and then we apply the power rule, so we will get 2 sec of t and then the derivative of sec of t, which is negative sec t tanh t. And so we get this function negative 2 sec squared of t tanh of t. And finally, we just get the derivative of the function 1 over the square root of 1 minus t squared. And that will give us t divided by 1 minus t squared raised to the exponent 3/2. Now, at this point, you may want to pause the video and calculate the second derivative of R yourself to verify that we get the correct function. Now let us look at this next example. So here, we are again given a vector valued function R, whose this time the coordinates are 2 plus ln of t, t sine of 1 minus t, and t cubed. What we want to do here is to find the vector equation of the line tangent to the graph of R of t at the point t equals 0. Now, how do we do this? First, let us recall that the vector equation of the line passing through the point x0, y0, z0 with direction vector v given by ABC is of the form L of t, whose coordinates are x0 plus at, y0 plus bt, and z0 plus ct. Now note that the point of tangent C, which lies on the tangent line, is the tip of the position representation of the vector R of 1. Okay? Now what is R of 1? R of 1 is the vector obtained by evaluating this given function R at 1. And so we get 2 plus ln 1, 1 sine of 1 minus 1, and 1 cubed, which simplifies to the vector 2, 0, 1. So we have this vector. Now the position representation of this vector will be the vector from the origin to the point 2, 0, 1. So we may take our point x0, y0, z0 to be the point 2, 0, 1. Okay? Now, recall that the vector r prime of 1 indicates the direction of the tangent line. And so we need to compute for the first derivative of r evaluated at 1. Okay? Now, the derivative of r prime of 1 will be the vector whose coordinates are the derivative of these functions here. So let us differentiate 2 plus ln t. The derivative of 2 is 0, and the derivative of ln t is 1 over t. So we get 1 over t. Now, for t sine of 1 minus t, we need to apply the product rule, and we will get sine of 1 minus t times the derivative of t, which is 1. And then we get, we need to add t times the derivative of sine of 1 minus t. But the derivative of sine is cosine, so we will have cosine of 1 minus t. And then by chain rule, we need the derivative of 1 minus t, which is minus 1. And finally, for the derivative of t cubed, we have we have 3t squared. And so all we need to do now is to evaluate this derivative at 1, at t equals 1. And so we will get r prime of 1 equal to 1, negative 1, 3. Kindly verify that indeed the derivative of r evaluated at 1 is this vector. And so we now have a point on the tangent line and the direction vector. And so all we need to do is to plug in this value here to this formula. And so we will get L of t equal to 2 plus 1 times t, and the second coordinate will be 0 plus negative 1 times t, and the third coordinate will be 1 plus 3 times t. And so the tangent line is given by the vector valued function 2 plus t, negative t, 1 plus 3t. Now for this slide, let us look at some properties of the derivatives of vector functions. So let us take f and g to be vector functions and take small f to be a real valued function. So again, f and g are vector valued functions, and small f here is a real valued function. So suppose that the vector valued functions f, g, and small f are differentiable. Then the following hold. Okay, the first result tells us that the derivative of the sum and difference of two vector valued functions is just the sum or difference of their derivatives. Okay. Now, for the second result, a real valued function f times a vector valued function capital F will yield for its derivative the following sum. Small f evaluated at t times the derivative of the function f of t plus the vector valued function f of t times the derivative of the small function f t. Okay. For the next two results, these two results can be viewed as product rules for derivative. So the first one is for the dot product and the second one is the cross product. And the two formulas are almost similar. So let us look at the derivative of the dot product of f with g. So the derivative is given by f dot g prime plus g dot f prime. Now, for the cross product of f and g, the derivative is given by f cross g prime plus f prime cross g. Now note that for number 4, the order of the functions in the cross product is important. So in particular, for the second cross product, you cannot interchange the position of G and F prime. So F prime should appear before G. Okay? And finally, we'll look at the derivative of the composition of F with small f. And this is the function f prime, the vector value function f prime, evaluated at the small f of t times the derivative of the function small f of t. Okay, so let us consider an example to illustrate the previous theorem. So let f be the function t minus 1 t cubed cosine t, and let g be the function ln t sinh t negative 4. Now we take a real valued function small f given by e of negative t. E raised to negative t. Okay? So we want to get the derivative of the dot product between f and g and the derivative of the composition of g with the function small f. Okay? So from the theorem, recall that the derivative of the dot product is just the formula given by f of t dot g prime of t plus g dot f prime. Okay, so what is this sum? Okay, so first we need to get the function f, which is t minus 1 t cubed cosine t, and get the dot product of this function with the derivative of g, which is derivative of ln t is 1 over t, derivative of sinh is cos of t, and derivative of the constant negative 4 is 0. So we get this dot product and add the result to the dot product of the function g dotted with the derivative of the function f, which is the derivative of t minus 1, so that will be 1, the derivative of t cubed, which is 3t squared, and the derivative of cosine t, which is negative sine of t. Now we compute for the dot products and we will get, okay, so t minus 1 divided by t, right? And t cubed times cos of t, which is this one. Now cosine of t times 0, we get 0. Then we need to add this dot product to the dot product of these two vectors, which is ln of t times 1, which is ln of t, and we have sinh of t times 3t squared, we get 3t squared sinh of t, and finally we need to multiply negative 4 and negative sine of t, which gives us 4 sine of t. So the derivative of the dot product of f and g is this blue function here. Okay, now for the second derivative, we want the derivative of g composition with small f, and by the previous theorem, this derivative is equal to the function g prime evaluated at f of t times the derivative of f of t. And so what we have here is, so we need the derivative of g, which is this vector here, 1 over t cos of t 0. Now if we plug in the function, the small function, the function small f to t, we will get 1 divided by e to the negative t cos of e to the negative t and 0 as our third coordinate. So we have this vector valued function times the function which is equal to the derivative of small f, which is the derivative of e to the negative t, And the derivative of e to the negative t is e to the negative t times the derivative of the exponent, which is negative 1. So finally, we get as our derivative the function negative 1, which is obtained after distributing negative e to the t to this first coordinate and multiplying this factor to the second coordinate. We get negative e to the negative t cos of e to the negative t 0.